Okay, in this lecture, we'll be discussing the concept of limits. This is the first of several parts, and here we'll focus more on the idea and we'll get into the details in more depth in the next couple lectures. But really, one thing to keep in mind is that limits are the primary tool of calculus. Limits are what make calculus different than the type of math like algebra or geometry that you've learned in high school. The real key idea behind calculus is always somehow related to the idea of limit. One way I tend to think of calculus is like construction. You use algebra and geometry to build something, and I think of that phase as using scaffolding. So you're building, say, a building, and you have all this type of scaffolding on it that makes it look very complex and sometimes kind of messy. Then we come in with the idea of the limit, and that is when we take the scaffolding down, and what is left is the nice, elegant building or structure. And it's always the application of limits that makes math calculus. So this really is the central idea. Everything that we do in calculus is coming back to the idea of limit. So first, let's talk about the idea of limit, and at the end of this lecture, we'll give the precise definition of limit. So, the number L is the limit of f of x as x approaches a. A can be any finite number. We'll also later write it or allow it to include positive or negative infinity. And we write it in this form. So limit as x approaches a of f of x. So that limit is equal to L if we can make the number f of x as close to L as we choose simply by choosing x sufficiently close to, but not equal to, the number a. So let's draw an example. And so this will be an example of a case where the limit exists, everything is fine and dandy. So suppose that we have our function graphed here, and then down here on the x-axis is a. And in this case, as depicted, this would be this value on the y-axis, L, would in fact be the limit as x approaches a of f of x. Roughly speaking, what this is saying is if we want to get as close to L as we want, so let's just say that there's some small window around L. So we want to get within this band of L. And we can say, all right, let's draw this as a band horizontally. So we want to get f as close to L. So, or rather, we want to get as close to L as we want, and that's depicted again by this blue band down here. If the limit as x approaches a in fact equals L, what we need to do is find an interval around a such that if we restrict ourselves to that interval, the function will always be within this band. So suppose now we say, okay, as long as you stay in here, now go up, we can see that it is in fact the case that, let's see, we'll do purple, the function in that band always lies, the function in this orange, if we choose x values in this orange band, so we don't care about this midpoint, we don't care about a. If we choose anything else in this open interval, then the function values, f of x, are actually within that blue band. They're as close to L as we had specified. This holds no matter how wide this blue band is. If you shrink this blue band down to something much smaller, then you would correspondingly shrink the width of this orange value, but the picture would stay similar. You would have this piece of function always being within both bands. So you're given the blue band, and then you choose the orange band. And that's really the idea. If the limit as x approaches a of f of x in fact equals L, this purple piece of the function will always be within both bands. So that's the way to think of it. That's the mathematical idea. Intuitively, you can think of it that as you cruise in towards a on the function from the right, and you cruise in on the function towards as x approaches a from the left, then you're honing in on this same value, L. Intuitively, that's another way that we can think of the limit as x goes to a of f of x being equal to L. Okay, there's the idea. Let's explore an example numerically, and let's think about this function here. Limit as x goes to 3 of x plus 2, of x minus 1 over x plus 2. And as we approach 3, let's just think about approaching 3 from both directions. So if this is our number line, and here's 3, and we're going to come in from the left, well, we can start off saying, well, what if we're at 2? Okay, if we're at 2, and we plug 2 into the function here, we get 1/4. Well, let's get closer. What if we're at 2.9? Plug 2.9 into the function and you get 0.387755. And we can keep getting closer and closer to 3 from the left. So 2.9, 2.99, 2.999, 2.9999, so on and so forth. And as we plug those x values into the function, you can see it looks like this is going up to 0.4. Similarly, let's come from the other side. So let's say start at 4. If we plug in x equals 4 to the function, we get 1/2. But we can also get closer. Say we go down to 3.1. And we get 0.411765. And we can get closer and closer, 3.01, 3.001, 3.0001. And it looks like when we plug these into a calculator that we're also honing in on 0.4, but we're going down to it. So that's our guess here, is that as we approach 3 from below, this is coming up to 0.4. And as we approach 3 from above, these numbers are going down to 0.4. If we were to graph this function, and this is something that we will learn how to do throughout the course, we'll see that we have a vertical asymptote of x equals -2 and a horizontal asymptote of y equals 1, and the actual graph of the function will look something like so. And we can see that if you were to plug in x equals 3, we'd be actually up here at 0.4. So what we've noticed numerically in our table is that as we cruise up this function from the left towards x equals 3, we're honing in on 0.4 from below. And as we cruise in on the right, from the right, we're honing in on 0.4 from above. What we would expect. Now it's worth noting, and this is a key observation, that this function could actually have had a hole here And if you had a hole here, and say the function had a value defined as a dot up here above it, the limit would still be the same. So what you're honing in on is you get arbitrarily close, but never get there, to x equals 3. Doesn't have to be the function's value there. So let's look at another example where this is illustrated. Here we have the limit of this, what we call rational function, when you have a polynomial in the numerator and a polynomial in the denominator. And if you tried to plug in and evaluate, so if you just, using what we saw here, we might have said, well, we could just plug in x equals 3, and we got 2 over 5, right? F of 3 in this case was 2 over 5, which is 0.4. And we noticed, all right, we just plugged it in and we got that value, and it turned out to be the same as this limit. If we try to do that here, think about what happens when you plug in 2. Specifically, look at the denominator. We would get 2 times 2, so 4, plus 2 times 2, plus 4. 4 plus 4 is 8, minus 8 is 0. So direct evaluation would lead to a 0 in the denominator, and we know we can't divide by 0. But in a question like this, what we can do is remember our factoring. So the top is the difference of two squares. Can be factored as x plus 2 times x minus 2. And in the bottom, we can factor that as x plus 4 times x minus 2, which enables us to then cancel out the x minus 2 terms. And now we see that there's no issue with actually directly evaluating this, plugging in x equals 2. And that is, in fact, how you do this. This is going to be 2 plus 2 is 4, over 4 plus 2 is 6, which is 2/3. We can take a look at this. We can look at the geometry and recognize the following. So if we plot this function, we have a vertical asymptote at x equals minus 4. And we'll also have a horizontal asymptote of y equals 1. And our function appears as such. Now the catch is, written this way, in the original form, we had a problem at x equals 2. Note that plugging in x equals 2 gave us this 0 in the denominator. And the issue then becomes that here we have a hole in our function. When we rewrite it, when we factor it and cancel out the x minus 2 in both top and bottom, if we just focused on x plus 2 over x plus 4, the graph would be the same, except there wouldn't be the hole. So geometrically, this is what's happening. And again, written either in this simplified form or in this original form, the limit is the same. The limit here, we noted that value is 2/3. And so it didn't matter whether there was a hole there or not. If you're coming in from the left, getting arbitrarily close to 2 for x, you're honing in on 2/3. If you're coming in from the right, getting arbitrarily close to 2 for x, you're also honing in on 2/3. It didn't matter that the function had a hole there. This is why we have the same limit in each of these cases. Another example, and this is one that we will revisit many times, f of x is the absolute value of x over x. And if you think about what this will be, we could figure out this right-hand side with a couple examples. Think about x being 2. If x is 2, the numerator would be 2, denominator would be 2. 2 over 2 is 1. There's nothing special about 2. Any positive number, that's going to work. What about a negative number? If x is minus 3, well, the absolute value of minus 3 is 3. So you'd have 3 over minus 3, which would be minus 1. So any negative number will be minus 1. And at 0, it's undefined. So the graph of this function, so remember, undefined at 0, anytime x is positive, this thing is equal to 1. But you have to put a hole here at 0. Similarly, down here at minus 1, for any x value that's negative, we have the function taking on minus 1. So this is the graph of this function. And one common limit to think about with this is, what about the limit as x goes to 0 of this f of x? And the issue is that, use the same kind of reasoning, and we'll make all these ideas precise soon, but as you come in along the function from the right, you're honing in on the value of the y value of minus 1. In fact, you're actually exactly equal to it. But if you are coming to 0 from the left, so the x value of 0, as we hone in along the function, we're coming in at a value of minus 1. Those are different. So this, in this case, does not exist. The overall limit doesn't exist because as x goes to 0 from the left, f of x is approaching minus 1, and as x goes to 0 from the right, f of x is approaching 1. And we would need these limits to be the same. You'd have to be honing in on the same value, whether you're coming from left or from right. This is a classical case of a function that has a limit that does not exist. If you picked any other value, like x equals 3, your limit would be 1. So for any other x value that you put here, you would have a limit that exists for this function. The problem is at 0, at x equals 0. In this example, if we plot things, this function, so we have a special case when x is 1. In all the other cases, this is just a line, y equals 1. So if x is different than 1, the function is just identically equal to 1. So we can draw our y equals 1. But then we note that when x is equal to 1, the function has a value of 4. So the function has this value here at x equals 1, so it has a hole in the horizontal line here. So in this question, if we're looking at the limit as x approaches 1 of g of x, as we're honing in from the right, the function is approaching 1. In fact, it is exactly equal to 1. So it's trivially, it's approaching 1. As we approach from the left, the function is also approaching 1. So in this case, we actually do have the result that this limit is 1, even though the actual function value is different, is up here. So the function value being further away, being what we'll actually call a removable discontinuity, but having the function value up here and a hole down here does not affect the fact that as you cruise in from the right or you cruise in from the left, you're getting arbitrarily closer to the value of 1, the height of 1. So, this was the idea of limit. To make things more precise, we want to give the official definition of limit. Suppose f is defined in an open interval containing a. So let's draw this as we go through it. It'll be similar to the picture we drew at the beginning of this lecture. And so here we have a, and let's have our function y equals f of x. And so the way this is drawn, and we should have a sense for it now, this would be an illustration of a function that does actually have the limit of L as x approaches a. So as we're cruising in from the right or the left, we're honing in on this value, vertical y value of L. So we say that this condition holds, the limit as x approaches a of f of x is equal to L, provided that the following condition is satisfied. And we're going to draw a very similar picture to what we had before. We're going to say, okay, we want to have this blue band around L, but what we're going to specify now is that the radius of this blue band, so half of its width, will be epsilon. So this distance here is this distance epsilon. Then, so we're given this epsilon. So we're told, can we choose an interval around A such that if we restrict the choice of Rx to that interval, then the function will sit inside this blue band. And so again, it's a very similar picture to what we had before. So now we will pick our interval here. But now we're going to say that the length of half of that interval is this value, delta. So this delta is the orange, and the epsilon is the blue. And so if we choose x to be within that A, then the function will sit inside both of these bands. That's what this is saying. If x minus a, an absolute value, is less than delta, that's the same thing as saying that x is inside this interval. So think of it as the distance between x and a. That has to be smaller than delta, so it's going to be somewhere in here. Then f of x minus L, think of that as the distance between the function and the y value of L. That distance is always smaller than epsilon. So that's saying the distance between this dotted black line and this purple curve, that vertical distance is always smaller than epsilon. That puts it inside the blue band. And if you give any epsilon, you shrink the width of this blue band, then you correspondingly only have to shrink the width of this orange band. And that's the technical, formal definition of limit. This is a good limit definition to think about. This is a good one to spend some time pondering, drawing some sketches to understand what's going on. Because really, this is the fundamental concept in calculus. So this is kind of the key definition in calculus. And this is taking the idea, our intuition that we just went through in this lecture, and making it mathematically precise. And so this is our official definition of limit. And again, the way to think of it is, if you are given a smaller epsilon, that just corresponds to shrinking this blue band, and all you have to do is shrink this yellow-orange band accordingly so that the function sits inside both. And if you can always do that, then that's by definition what it means for the limit as x approaches a of f of x to be equal to L. So we will follow up on this with more coverage of limits in the next lecture.